Okay, hello everyone. Welcome back to our first Oxford seminar for 2026. This week we're hearing from Adrian, who will be giving us an overview of Petri theory.
Hello, everyone. I've been discussing with Jason for a bit about, the Topas's take on PetriNet with the whole view of, the symmetric monoidal categories and such. And I realized that there's very few, in this view, there's very few that we take back from all the theory that's been developed over 5 decades. And so I wanted to give an overview of what's been done classically in the theory of Petrinets so that we may draw bridges with this categorical view as monoidal categories. So I took the liberty to draw some material from this book from Eikebest and Raymond de Villers. So they are two of the most notorious contributors to the theory of Petrinets, and they very recently did this textbook that gathers careers of experience in teaching the subject. So I wanted to promote it a bit because they're I look up to them a lot. Okay, so this is a Petri. What's a PetriNet then? It's a form of graph, as you can see. It's directed, and it has 2 classes of nodes. The circles are called places, and the squares are called transitions. Now, the places are essentially static in nature. We'll use them to represent states of a system, whereas transitions are dynamic. They express how the system evolves with time. A PetriNet in itself is bare of states, so it's just a layout. And we'll speak of a PetriNet system when we define the notion of states on them, and then the execution semantics that comes with it. Fine. So I think I'm starting with the most basic classes. I think. Okay. Yeah. So this is a bit historical as well. Originally, Petri envisioned that the places would represent conditions, and placing a token in a condition would represent the fact that it holds at a state, whereas not having a token means the condition does not hold at that state. So a state is defined by putting tokens in the conditions that hold in the initial state. And the states are characterized by the set of conditions that hold at them. So the arcs can only link transitions to places or places to transitions, meaning there are never arcs between places and never arcs between transitions. And they indicate a flow. So the idea is that they will tell us how the tokens move around the system as it evolves. Now, before getting into this, I wanted to give a bit of draw the landscape that exists in PetriNet. So in general, the places could contain anything, right? So as we've discussed with colors, you could imagine any kind of data values that move around or processed by the transitions and such. Now, in the most basic models, they are either Boolean, meaning 1 token per place, or a natural number of tokens. Okay. And in particular, a net is called safe when the values are Boolean. Okay, so It's a way to say that we don't allow for arbitrary numbers of tokens, only one per place. Another structural property that's very relevant is when the net is pure. So the net is pure when given a pair of transition place, the the edge only goes in one direction. Okay, so if I have an edge going from a transition to a place, then there cannot be an edge feeding it back. Okay, and this will be very important in terms of complexity later. It makes decidability of some problems way easier. Now it's called plane when all the weights are one, in which case we don't even draw a weight. I will explain these semantics later, but for now, just keep in mind that we have these structural properties when seeing them as graphs, okay? So the edges could be weighted, but we can also forbid them, in which case we say the nets are plane. And simple. This is, well, it comes from a very, how will I say this? Well, Petri insisted a lot in this property that events should be characterized by their observable effects. Actually, when establishing the theory of Petri nets, he said this as an axiom. Meaning that if, for example, A and B have the same input places and the same output places, then there must be the same transition, okay? So in this case, I want to distinguish them, meaning that I have to, describe a place that has a different relation with one of them, okay? So by adding this place, then I'm making the net simple. Right. Now execution semantics. Well, I have a state. This is, again, an elementary system, meaning that the places represent Boolean conditions. So at the initial state, P1 and P2 hold, and no other place holds. And I can see that T1 has P1 and P2 as only input transitions. And since they both hold, then T1 is enabled, meaning it can fire. And when it fires, it will consume the tokens from the input places and produce a token in the output place. Now, this means that the post condition now holds and the preconditions don't hold anymore. Okay, and this is very reminiscent of Hoare logic if you give it a bit of thought. Okay, so now T2 was enabled and it fired, right? Now, an important feature of Petri nets is what we're seeing now. T3 and T4 are both enabled. Okay, and when I fire T3, I think I fire T3. No, I don't. But if I fire T3, T4 remains enabled and it can also fire. And actually, T4 may fire before T3 and it would reach lead the system into the same state. So this is exactly what we call concurrency. I will get back to that later. Right. So I was discussing structural properties, and this notion has come up in a lot of discussions within the area groups. So I wanted to make a specific slide to explain this, because it brings in a lot of problems when doing analysis on the net, and especially when trying to define probabilities in such a way that the traces have consistent probabilities. So confusion is problematic in our setting, in the whole ARIA program. For instance, so what is confusion? Confusion is this sort of situation where I have two concurrent transitions, but the firing of one unrelated transition can withdraw this concurrency. So we see here T1 and T3 are concurrent. If I imagine a token here and here, they could both fire independently. Okay. Now the problem is that T2 is in choice with both T3 and T1. Okay. And the fire, so here I could focus on the choice here between T1 and T2. Choice means that if I fire T1, then T2 cannot fire, and vice versa, right? Now the problem here is that I have a choice between two transitions that can be disabled by the firing of a concurrent one. Okay. Now this is problematic because a choice is essentially local. Okay. In order to describe a choice in my system, I basically need to impose that they share a common variable they depend on. All right. Now the fact that something remote, something concurrent, meaning it happens in a different computer, can suddenly affect the fact that the choice is there or not, is extremely problematic. Okay. This is what we call confusion then. And the solution that was provided by, I would say, many years of exploration and research is free choice nets. Free choice nets are exactly the nets in which choices are never conditioned by something remote, okay? So, for instance, here I have a choice, but it is conditioned by a precondition of T2, right? Yeah.
Just to check my understanding, these dot T1, that's the precondition.
Yeah, sorry, I didn't stop on this, but it is indeed. So this is the set of input places for T1 and the set of
So if they have any shared input, they must have all shared it.
Absolutely. That's what it says. Yeah. So for instance, here you see, yeah, so T1 and T2 are in choice only when this place is marked, right? This place is not marked, then only T1 can happen. Okay. And this is the kind of situation we want to forbid in a free choice net. We say the choice is conditioned by this place. A free choice net is where no choice is conditioned by any place. Okay. And the way to solve this is just by making sure that all preconditions of all transitions in choice are shared. Okay. So there are no places conditioning the choices. Okay. Good. And yeah, so this, in general, these nets, when this property holds, they're extremely well behaved algorithmically. Problems are solvable much faster usually.
So just to check I understand correctly. So this is like a subset of the net. For the full net to be simple, you need T1 and T2 to have different those conditions. Right? Because there are others that have the same effect.
Absolutely, yeah. Which in turn okay, I won't get into that kind of detail, but if you impose this in a, so there are other structural conditions that let you guarantee that the net is safe, so no place will ever contain more than one token. And if you combine the two, basically the whole system degenerates, and what you get is a finite state machine. So you get rid of all concurrency, basically. So in some instances, it can be really overkill to apply this kind of condition. But on other instances, it doesn't affect that much. So if you don't impose the nets to be bounded in that sense, it really helps and makes everything very well behaved. Okay. Good. Oh yeah. So thanks for the note. This slide should have come earlier. Thank you. Yeah, but it's exactly. So this was the question. So the preconditions are the places such that there is an arc to the transition. And symmetrically, we write the dot to the right to express the output places. And importantly, we say they are independent when they share no pre or post condition. Okay, and this is one requirement for concurrency. Okay, the moment they share one precondition, one post condition, this means that there could be a state at which they are not concurrent. Fine. So on top of independence, in order for them to be concurrent, they need to be enabled at some marking. Okay. So here, okay, so I'll show the notion here. But first, let me talk about the marking graph constructions, because I'm starting to talk about semantics now. Now, Petri nets are a dynamical model. If you want to see how the system evolves, you actually have to run it. Okay, they don't tell you anything about the behavior of the system unless you actually play the token game, meaning you move tokens around by firing transitions. So how do we express the behavior? There are several ways, and one of the most standards is the marking graph construction. So in a marking graph construction, I'm basically identifying each distribution of tokens with a state on a graph. So here, a vertex on this graph. So each such state is also called a marking, because it corresponds to the marking of places in the net, okay? So here I could essentially write M1 equals P1, PC, P4, okay? To express the fact that these are the properties that hold at this state. And now, as I can see, at this state, both T1 and T5 are enabled. Okay, so T5 has a token in all its input places, also T1, so they can fire. Now you can easily see that the two are independent because they share no input and output places. And so since there is a state that enables both, we say they are concurrent. Okay. And in this case, what we see on the marking graph is that if I fire T1 and then T5, or first T5 and then T1, I will reach the same state. Okay. This is what we call an interleaving of T1 and T5. And as you can see, independently of the order, I would reach the state in which P5 and P2 are marked, okay, which is M5. Good. I think I have all the notions here. Yeah, okay. So similar situation is with a choice. So a choice, as opposed to concurrency, is also when two transitions are enabled at some state. So here I have T4. Okay, from M5 here. So suppose I fired T1 and T5. I should update this slide. So I'm on M5, and now all the preconditions of T2 are enabled, and all the preconditions of T4 are enabled, so they can also both fire. But they share one precondition here, meaning that firing one will prevent the other one from firing. Okay, and this is what we call a choice. Okay. So they are not independent, but they are also enabled at some state. And well, that's the difference between a choice and concurrency. anything else I needed to say here? Oh yeah, deadlocks and liveness. So a deadlock is a state of the system in which nothing is enabled. Okay, M8 or M6 here, which correspond to either P3 or P6 being marked in some state. And liveness is the dual notion. So we say that a transition is live in the net if from every reachable marking, I can reach another marking that enables it. So no matter at which state of the system I am, the transition can eventually reach a state in which it fires. Okay. What's nice about Petri nets is that I represent, instead of representing concurrency with this interleaving of events, I just represent it by having two transitions that are distant from each other in some sense of distance. And this has the advantage of reducing the size of the system a lot in the presence of concurrency. So, well, the size of the system, I would say the size of the representation of the system, because they actually represent the same system. So the system will just have the same number of states. But here I can represent it much more succinctly, because, well, each transition is represented only once, essentially, okay? So here I didn't add the labels, but I have essentially three components that are just loops. So each of these will correspond to a loop in one direction. And so if I focus on this one here, regardless of the state of the others, the loop will be the same here, okay? Same goes for this one, just another dimension of the cube here. And this one, okay, just the depth of this cube. As a result, here I have three components of size n, well, size 2 in this case. And the system, instead of a product here, gets a full exponential, right? So with three components of size 2, I get 8 states. Okay, this is what we call the states explosion problem. And it's especially tricky when it comes to verification, because I can draw a fairly simple model here with a Petri net that has a huge behavior on the other side. And known techniques for formal verification usually apply on these kind of models. And, well, you know, they're very, very resource expensive. So this can be problematic. Okay, so now we go to the next class of nets, which is I just allow for as many tokens as I want in each place, okay? So now I have a natural number of tokens in each place. The arcs are now weighted, meaning I can say, well, this transition will consume 5 tokens from this place and produce 7 tokens in the other. And actually, the firing rule becomes that all the preconditions must contain at least as many tokens as indicated by the arc, the corresponding arc. And when the transition fires, well, it will consume what's indicated on each arc and produce what's indicated on the output arcs, okay? So that's very intuitive. Now, the thing is, with this kind of semantics here, we can now get infinite behavior, right? So there's no guarantee that the net will keep a finite number of tokens indefinitely. And actually here, kind of drew it. This would continue replicating this shape forever here. Fine, so here's where we get to vector addition systems. Vector addition systems were actually developed in parallel to Petri nets at a very similar time. But Petri nets were being developed mostly in Germany, and this other view as vectors was mostly in the United States. So basically, this view of vector addition systems, it's just that now I can just see every place as the dimension of a vector, and I will put just integer values on each coordinate, actually positive values. With this view, I can now view transitions as the vectors that consume from one coordinate and produce to another. Okay. But this leads back to the structural properties I was giving earlier. In order for this to hold, the net system needs to be pure. Okay, so I cannot have an arc going in and also coming back, because I could not define this number. Okay. And now basically the dynamics is I can add these vectors as long as I don't get a negative coordinate on my states. Okay. And then I can just go on adding vectors. When I have concurrency, we were discussing this earlier, summing one vector after the other has the same effect as the other before the first. And I could actually just add the sum of the two vectors altogether, and this would constitute a step. Okay? But it's not possible to do so at any state, because one of them might generate a negative coordinate. Okay? Whereas firing the other first, and then this one could be perfectly acceptable. Okay. So some steps are allowed when the transitions are concurrent. And if they constitute a choice, well, then the step is not really a valid, transition. Okay. Cool. Now, another class of semantics that was studied for this is the notion of trace. So this relates more to the kind of, what's the accepted language of a Petri net? Okay, much like, regular languages are accepted by regular finite state automata and so on. So there was a whole line of research regarding this. And what became fairly standard is the notion of Mazurkiewicz trace. So very intuitively, firing sequence is just a valid sequence of firings, meaning if in order for the transition to fire, it must be enabled at the corresponding state. Okay, so now from the initial state, T1 was enabled, so I can just write it in my sequence. At P5, T2 was enabled, and I can fire it. So here I could not add T1. This would not be a valid firing sequence, okay? Now I can fire T3 and T4, and so on. I made the initial state again, so I can basically just loop forever here. Now another firing sequence is just starts the same way, but now instead of firing T3, since T3 and T4 are concurrent, I can fire T4. And then fire T3, and then I'm at the same state again. Which means that not only these two can loop forever, but I can actually do combinations of these two, and all of them are valid firing sequences. Now, in order to encompass all these notions, comes the idea of a trace. That when two transitions are concurrent, I just don't mind how they are ordered. So I just say, well, here, I don't mind. It's a set. I could fire one and then the other. I could fire both at the same time. I could, the order becomes irrelevant. And this is what we call a Mazurkiewicz trace. So I didn't put the full formalization here, but they're actually defined as equivalence classes on the firing sequences, okay? So equivalence classes up to the equivalence relation defined by interleaving on the marking graph, okay? Cool. So, yeah, so this is now, like, it has become the standard formalization to discuss accepted languages of Petri nets, okay? So now another notion of semantics, and discussed this some weeks ago, is the notion of unfolding, okay? There was a very a historical paper called "The Semantics of a Net is a Net." And the whole idea is that when you have a net system, you can describe its behavior by an infinite net that has no markings now. It's just a net, okay? And here's how it works. Starting from the initial state, I represent each token in the initial state by a place in the net. But the place here doesn't represent this place. It represents the fact that this place contains a token. So in particular, okay, I will get there later. And now if a transition is enabled at this state, I will draw a corresponding event now, which is not the transition, but it's labeled by the transition, that has the same incidence, okay? And then for each token this produces, I will draw the corresponding place that now represents the fact that this place contains a token. Again, so transitions don't represent transitions. They represent the fact that a transition is fired, okay? And the places here correspond to the fact that the place contains a token, okay? And we continue, and we unfold the system. This is why it's called an unfolding, okay? Now, I don't know if I have the time to go over all the details here. Yeah.
So I start with a marking and then I unfold the system from that marking.
Absolutely. Yeah. Okay. So, okay. Let's go over a few notions. This is directed acyclic graph. Okay. Now, meaning it has no cycles. If a place, a token ends back at the place where it started, I would represent this by a different instance of the token being in that place. Actually, I interpret this token as being new. It's not the same token moving around. Every transition consumes tokens and produces new tokens. Okay. How can I find the states, arbitrary states of the system in the unfolding? Well, there are cuts, okay? Meaning, so this is a DAG. The flow relation describes a partial order, okay? And a cut is essentially an anti-chain, okay? That is, only has one kind of nodes. So either it's all places or all transitions. Now, okay. Choices. I can see the choices clearly here because I have branchings at places, okay? So when I have a branching at an event, this essentially represents the fact that I'm spawning a thread, okay? The process is being divided into sub-processes and so on and so forth, okay? When two threads are spawned like this, they are allowed to merge back at some point, okay? This is just synchronizing the two threads again and continuing. However, when there is a choice, meaning that the partial order branch is here at a place, this really corresponds to different processes being depicted. So I would have to, if I wanted to see one single evolution of the system, I would have to pick one of the branches here and see what follows from it, okay? Now this is what we call conflict, okay? Meaning that whatever I find in the system that I can trace back to having branched over a place is in conflict. They don't belong to the same process. Okay, they represent different executions of the system. Now, a state is a maximal antichain, which is conflict-free. Okay, so here this is a valid state. This here would not be a valid state because it contains conflict. So the states are actually either this or this, right? But more than this, this is an antichain here, but this is also an antichain here. Okay, corresponds to the fact that T3 is independent from T1 and T2. So it doesn't matter if I fire these first or this first, I will eventually reach the same state.
Sorry, you're saying S3, S4, S2 is a conflict-free anti-chain?
S3, S4, S2 is a conflict-free antichain.
So
yeah.
The fact that we split at S1 and went down.
Oh yeah, no, you're absolutely right. It's either S3, S2 or S4, S2.
I'm sorry. Okay.
Well spotted.
Is a state a maximal conflict-free anti-chain or a maximal anti-chain which happens to be conflict?
No, a maximal conflict-free antichain.
Okay. So like S2 and S4, that's an anti-chain, and
you cannot extend it without adding conflict,
okay.
so you're good.
Okay.
Yeah. And dually, if you a maximal conflict-free antichain made of transitions, events in this case, corresponds to a step. So it means that you could actually fire them together. Okay. But if the antichain contains a conflict, then that's not a valid step. Cool. Fine. And I added this slide because of Alex Stalk, you know. I don't know if you saw the thing in ambi vibrations. But he mentioned this very classical chapter from Nielsen and Vinskell about that's called models of concurrency, where they go through all these different semantics and show how they are related together. And one particular instance is about event structures. And there's a very natural transformation from this kind of unfolding of semantic representation into an event structure. So I already went through all these notions. There's causality, is just the transitive closure of the flow. It's a partial order. And conflict is in the having branched at a place relation. So it's you define E4 to be in conflict with E5, and then you do take the closure by causality. Okay, so once you're in conflict, whatever happens next will remain in conflict forever. Okay. And yeah, and you define parallelism as the residue of causality and conflict. So Two things are parallel or concurrent when they are neither in causality relation nor in conflict. And now you can basically keep this information. So these are just binary relations defined on the set. And it turns out that once you have this information, you can actually forget about the places. Just stick to the events, keep the labels, and keep the relation. So now you keep the information that E4 depends on E1. You keep the information that E8 is in conflict with, no, sorry, E4 is in conflict with E5. And you can erase all the places. It turns out that that's perfectly fine. You could retrieve those places if you wanted. Okay? So basically, this kind of information is enough to describe the process. And what you obtain actually after, so by keeping these relations and erasing the places, is exactly just an event structure. So I didn't give the formal definition here, but it's a set of events, a causality relation, and a conflict relation. And that's it. Okay. And in this case, if you add the labeling, you get all the information you need on the system.
Is it easy to describe how you get back the places just from the event structure?
Well, yeah, it's just you need to have a place between each pair of events that are causally related. And if two events are in conflict, you can actually trace back the conflict to the initial events that generated the conflict, and you say, okay, there's a place at which they branch. It's fairly easy.
You might not record the same map, right? Because we're using different.
Absolutely, very well spotted. This is why it's only a co-reflection and not a full duality. But at least there's an adjunction. Yeah. And the fact that it's a co-reflection actually is telling you that different unfoldings can lead to the same event structure. And the fact that there's an adjunction also tells you that given an event structure, there is a standard canonical way to retrieve an unfolding. Okay. Cool.
Is there no characterization of those unfoldings which are generated by event structures? Like, can you recognize when you said it's co-reflective and unfolding?
Yes. So there's there is, they're called prime event structures, but not only. So the key thing is you need causality to be acyclic.
Or causality to be acyclic?
Yeah.
Do you not have that property?
Not in a general event structure.
Oh, okay.
Maybe I didn't understand the question.
Sure. So, which is co-reflective in which? Unfolding that's co-reflective in event structures, or
So what I can tell you is given one event structure, there are several unfoldings that generate it.
okay.
So that should tell you which side
Right,
is
okay. So you can always build an event structure from an unfolding, and it will be
absolutely.
subclass of event structures.
Yeah, but there are some event structures that do not correspond to any unfolding.
Okay.
But they are fully characterized though. So we know how to spot event structures that come from this.
Okay. Okay.
Okay. Same goes for transition systems and Petri nets in general. So here, this kind of representation is a transition system. And this class of models is much larger than this class of models, okay? There are way more systems you can express in this way than with this, but we know how to spot them.
Okay.
We don't need to have the net in order to tell, oh, this is a good one. There are full characterizations around. This took decades and a lot of effort, but they did it, you know.
Right. Because that says, so maybe it's a better question for the end, but we talked about like the language generated by PetriNet, and you're saying you can always build a label transition system corresponding to the PetriNet whose language is the same. That's saying languages for PetriNet are sort of less expressive, or at most as expressive.
No, absolutely. They're less expressive, yeah. Yeah.
Or precisely as expressive, because it seems like you can also go backwards and build a.
No, you cannot always go backwards. That's the thing. If you give me an arbitrary graph here, it's not true in general that it comes from a PetriNet.
Could I just like.
I mean, not the models I'm presenting now. There are extensions of PetriNets that are expressive enough to express all kinds of transition systems, but we need to add colors.
Okay. I thought if you just stick like a transition where every edge is labeled by the edge.
Yeah, but the thing is, you need the labels to be in perfect correspondence. So I want these two to be represented by a unique transition.
Okay.
This is the key. Jade so had the exact same reflection.
Okay. I think
because you would be tempted to just draw a transition here at every edge and say, okay, this is a PetriNet. And it's true if you label the transitions, but that's sort of cheating. You're saying, well, I have different effects representing the same action. This is actually how we go about non-determinism. I could talk about it in another talk if you want. It's actually a very, very interesting subject. Okay, event structures, we covered that. What has been studied on PetriNets over the decades is this kind of problem. Give me a PetriNet. Can I know if it's bounded? Meaning, actually find out if it has infinite behavior or if, eventually I will end up with a finite number of states cycle around well, in the general case, so here when I say the general case, this means PT systems and tokens, okay? Of course, boundedness, if the net is safe, is trivial because they are all bounded. So deciding this is XSpace complete, and if I don't have choices, I never branch over places, and thing trivializes. Speed time. Coverability, maybe I think I will skip coverability. It's very interesting, but I don't think I will have the time. Reachability is by far the most studied problem. And the general case eluded researchers for 40 years or something. It was proven, it was known to be decidable, but the exact complexity was still unknown until very recently. I think 5 years now. In general, primitive recursive space, right? So like Ackermann space, like it doesn't fit the universe, right? Right. Interestingly, if you allow for zero tests, and I think equivalently inhibitor arcs, this is maybe something I should have said. So I'm going to get back very quickly to this one. Where is it? Here. Yes, so vector addition systems. If we allow for other operations like, reset, zero tests, what we get are counter machines, right? This is Turing expressive suddenly. So all the things that were in the slide that I was showing you, all of this becomes undecidable. Like you cannot decide reachability in a Turing machine or boundedness, or you can basically decide nothing on a Turing machine. So the moment you add zero tests, reset arcs, inhibitor arcs, these things become crazy, right? These problems just tend to be undecidable, and if they are decidable, they're like the complexity is like out of this world. Fine. Nice results is that if you limit the number of places to be at most 5, but then you have all like a bunch of transitions that can have wild effects, but only on 5 counters, then there are reduction techniques to 2x time, which I find is pretty cool. If the nets are safe, then p-space complete. This is reachability again, so maybe I should have explained what the problem is. Given a state, can I reach it? So is there a value of the counters that can be reached eventually by the execution of the net? And you would think, well, if the net is bounded, I can just inspect it and so, but it turns out that I need to save a lot of information on the way, and the thing is actually p-space complete. NP complete if you don't have cycles or the net is conflict-free, meaning it has no choices. And this result actually comes from structural analysis. I will get back, I have a few slides on it. And then the good stuff. If the net is bounded and has no choices, trivial. If the net is a marked graph means that each place has only one, is only output to one transition and input to another transition. So no place can branch, and 2 transitions cannot feed the same place. Also trivializes the problem. And if I know that they are live, bounded, cyclic, and free choice, then also I can check. But this takes a lot of X-space here stuff. So it's actually, you know, you already have a lot of information that was very costly to obtain. Cool. And then liveness, again, this, in general, it's a reduction to reachability. But by inspecting the structure of the net, in some cases, you can do a bit better. The general complexity is unknown, so we don't know the exact class. Okay. If the nets are safe, p-space complete. Free choice net, here they pop up, co-NP complete. If the net is bounded and bounded free choice, I did not explain, but free choice comes up again here, the picture. It trivializes things, you know, free choice is very cool. And then conflict free, again, p time. And yeah, just checking if it has deadlocks is the dual to liveness. So complexities differ a bit, but they're in the same vibes, right? Fine. So all of these are decision problems. I want a crisp answer. Is this true? Yes or no, right? But if I'm fine with finding sufficient conditions, there's actually way better that I can do. And here I really wanted to talk about this because I think this is one of the coolest things of Petri nets, is that you can actually analyze the graph structure of the net and decide a lot of stuff just by doing linear algebra, right? In like Gaussian elimination, it works. So in order to do this, you need to work with the incidence matrix of the graph, which is very nice when the net is pure because it coincides with a flow relation. But when you allow for arcs going in 2 dimensions, then it will not tell you as much on the system. You're sort of losing information. And actually, if you consider only the incidence matrix on a non-pure net, the resulting behavior will over-approximate the one of your system. This means that you will suddenly allow for things to happen that should not be happening, okay? And it's in this sense that doing the linear algebra on this on an impure net is giving you normally sufficient conditions for things to hold, but not the full characterization. Nice. We will use this matrix to look at, cycles, cycles made of places, cycles made of transitions, this kind of stuff. And invariants, right? And we will do so by looking only at the matrix. So no states on the system. We're only looking at the structure. And so what we will be checking are what we call structural properties, meaning properties that hold independently of the marking, okay? So for instance, a net is structurally bounded if for any marking, the resulting system is bounded. No matter what the initial marking, it will remain bounded. Dually, it is structurally live if for every marking, the system is live. So we say the system is live if there is some transition that is fireable at every state. Okay. Eventually fireable. Oh, okay. And this kind of things is what you can do with structural analysis, right? Turns out the net is structurally bounded. If I can find a vector that has no null components, all components are strictly positive, and it solves the following system of inequations.
What's T? Is there some?
The transpose.
Oh,
Right? So this means that really what this says is there is a marking in which the global effect of the system takes tokens from it. I found some marking that somehow allows for all the behavior that I need to see. It has to be large enough that I see everything happening by running things only once. But then if the global effect is negative on all places, and so on, I know that eventually things are consumed. Like this is like saying tokens tend to disappear. Sorry, past. Tokens tend to disappear, right?
so it's less than equal to 0. That's saying on like every.
Tend to disappear.
Okay. So that's the C transpose dot X is a.
So the matrix is, you transpose it because this is a vector that corresponds to a marking. If you don't transpose it, you're sort of saying, I want these transitions. So the coordinates of the vector would be transitions. And you're saying how many firings of each transition I want. In this case, I start off the marking and I fire everything once. Okay? And if I find a marking in which I fire everything, and firing everything once just consumes tokens everywhere, then that guarantees that the system is bounded. It's actually an if and only if. It is more tricky. You need to show that, you relate every marking to this in some way. Cool. And dually, you have this thing. So now this vector is made of transitions. It's what we call a pyrrhic vector. So basically, each transition is now a coordinate. I'm indicating how many firings of each transition I'm considering. So this vector actually represents a firing sequence. It's just that I'm not giving a specific ordering. Just saying, well, any firing sequence in which T3 fires 7 times, T2 never fires, and this kind of thing. So there is a marking, the statement is, there exists some marking from which the net system has an infinite firing sequence if and only if this property holds. And the property is that, so now I don't require this to be strictly positive in every coordinate. I'm requiring that at least one transition fires, okay?
Okay, so y greater than 0 is not saying.
Here, I require that for every coordinate, the vector is positive. Here, it's weaker. Here, I require at least one coordinate to be positive.
Yeah.
Okay, and no coordinate to be negative, of course. And then if, so now what I'm looking at here is the effect of the firing sequence of the system. Okay. The effects of, so I'm finding a vector that corresponds to a set of firing sequences. It represents some firing sequences. And the overall effect of the firing sequence is producing tokens on the net. Then, since I only produce tokens, the same firing sequence will still be applicable.
Or it's just not consuming tokens or something. So it could be equal to 0.
It could be equal to 0, because then this would mean that after firing this sequence, I would end up exactly at the same marking. So if it's equal to 0, then this vector is actually called a T invariant. It corresponds to a loop in the system. Just like a firing sequence that returns to the same marking. And I didn't go any further, but indeed, this goes very deep. Like, it's what we call structural analysis, and it goes into place invariants, transitions invariants. What do they tell you about the system? What do they tell you about the graph structure? What do they tell you about the behavior? Okay, place invariants somehow tell you stuff about how you can distribute the system. They tell you where are the sequential components, right? What is actually runnable in parallel, what not. The the transition invariants, they're telling you things about looping behavior, returning to the same point, this kind of stuff. And then you have, as you're doing graph theory, you identify sources, sinks, this kind of, there's a whole bunch of things you can do. The book I presented earlier has 4 chapters. So like, 70 pages of structural analysis. And I mean, this book is really, it's an undergraduate textbook, right? So it's very, very easy to read. Has exercises that are actually a bit boring to do, but it's very, very, how do you say, comprehensive. It covers really everything that's been done to some degree of detail. And getting into the last chapters, you actually get the saucy stuff, like the proof of complexity of reachabilities in there. And that's a tough one to write, and it's a very tough one to explain to the undergrads. And I must say, like, Beston de Villers did an excellent job there. So I recommend to have it on your desk if you're going to do Petri net theory. Maybe not reading it, but having it at hand to consult it and so on. And that's it.
Okay, let's thank Adrian for his talk.
How long did it take?
That's pretty much, we started late, so that's right on time. And are there any questions for Adrian?
Yep.
That's great. Thank you for that. It was really helpful.
Cool.
Let's see. So the slides you covered at the very beginning describe this. We have these. You focused on PT nets, not to be confused with Petri nets, because they're a particular kind of
PT systems, right?
PT system. And before that, you covered what were they called?
Elementary net.
Elementary nets. So those are like sort of, they either have a marking or they don't, and the next one is they have a number of markings.
Yeah, right.
I've been hearing about a large number of different adjectives that can come before the word Petri.
Yeah.
How do some, so for example, stochastic dynamically colored Petri net?
Yeah.
Thing. How do these kinds of things, which are incredibly more complicated, they're all Turing complete, probably, at least.
More, I think more.
Yeah, they're incredibly complicated. How did
Expressive, yeah.
how do those kinds of nets relate to some of the techniques you've talked about here? Do you?
Well, that's a very tricky question, actually. I'm not sure. So, first of all, many of these things are like too new to have been studied in depth. So I know what I can tell you is, for example, colored Petri nets in the presentation of Jensen and Christensen were actually designed so that all structural analysis comes through. So the cool stuff you can do with linear algebra, you can do on colored Petri nets. Okay. And actually, it took them a while to get there. They started with something called predicate nets. There were some problems with the execution traces being too dependent on the guards. And they came up with the idea that that it should be a type system, right? And the fact that instead of predicate logic, you have lambda calculus, this suddenly makes all of linear algebra go through. It's like magic. And it's very brilliant that they reached this point. And colored Petri nets were designed on purpose so that this happens. Okay, so they were looking for an expressive model, but designed in such a way that all the structural analysis would go through. And it does on colored Petri nets. Stochastic nets, so honestly, I know there's work done, especially on verification. But I can't tell you how much of this has been transferred to it. And essentially, I think the general approach with stochastic nets is I just unfold the thing. So I find the equivalent of a transition system, which is actually you end up with Markov processes or in general MDPs. And then you analyze the MDP, but of course you have state space explosion and it's a deal. So the kind of use as you do of Petrinet theory there is more like in having a modular description of the MDP that lets you tackle the state space bit by bit, instead of having the general product that makes things super large, right? So it's more about the modular composition, I would say. And honestly, the CPNs are too new, and I guess it would be exciting to see what happens. I think it needs machinery. So as it is, I don't think any of this can go through. But I'm have a few ideas on how you could, you know, split the problem into chunks and go bit by bit.
Cool.
So,
Thank you. Thank you.
but that's future work, I would like to say. We haven't even started.
Cool.
Yeah,
Thank you.
you had a question.
Yeah. So I'm relatively new to Petri nets. It's like basically my first introduction to them. So where do they usually pop up in the wild?
So, okay, so they became very popular as a modeling tool because, you know, they're very, I don't know, I guess engineers like them, you know, they're very visual. And they have this advantage that they're like a layout of the system. Like here you see the behavior of the system, and it's like not so easy to parse, right? Here you can interpret this like geographically. You know, this is a computer here. There's another computer here. They synchronize here, and they share information here. It's like you see actually a network and how it's distributed. So it comes up in modeling a lot. So a lot of papers are about, I used Petri nets to solve this problem. Okay. A lot of scheduling, uh, um, yeah, I don't know, you know, planning, manufacturing, model, I don't know, what did I read? Something, it was oceanography. They came up somewhere. I mean, you find the weirdest applications. Like people have this very wild imagination on where to use a Petri net. And I would say, from a theoretical perspective, you will see a lot of papers about this stuff, studying the complexity of this particular subclass. Can I gain something by taking, you know, adding this property, and maybe I can, you know, get rid of an Ackermann, go back to X space, this kind of stuff. You'll see a lot of theoretical papers about, you know, complexity. And I think they're very interesting models in that sense, because of what I said earlier, right? Like, if you think of Turing machines as counter machine, and you just forbid operations. You say, okay, what's a counter machine without zero tests, without resets? What if I forbid this kind of behavior? What if I forbid this kind of behavior? And then suddenly things become decidable that were not. Maybe things were decidable, but, you know, non-primitive recursive, and suddenly they become X space. And this kind of thing is like super interesting and makes like Petri nets like a very, I would say, very powerful tool to draw the landscape of complexity. Because it's really a formalism that lets you add feature, take out a feature, add a restriction. And it's very close. If you take the view of vector addition system, it's really very close to counter machines. So I think it has inspired a lot of theoretical developments in complexity theory. And yeah, I mean, from the theoretical perspective, I think this is the main interest. And then like loads and loads of applications, you know, they're used to model problems. And since we have all these techniques to, you know, say things about the models, like if you can derive a Petri net, if you can encode your problem as a Petri net, then you have 4 chapters of the book to say about your problem, you know? And you can apply techniques, algorithms that work. So it's very fruitful in that sense, right? But I'm going to say that it mostly comes from structural analysis. Like structural analysis is a toolkit. Like if you manage to model your problem as a Petri net, then suddenly you have a whole toolbox on your desk and you can use it to study your problem, right? So it's what makes it very popular.
I have a question about structural analysis. So you said it gives you these sufficient conditions for boundedness and lightness.
Yeah.
Does it simplify the reachability problem, or does it provide sufficient conditions for that? And then,
Well, not really.
Sure.
Yes, it does if the net is pure.
Okay,
If this matrix actually is this matrix.
right, okay.
The problem with reachability is that here you're over approximating behavior.
Mm.
So whatever you're like, say you could find reachability thanks to structural analysis, unless the net is pure, what it's telling you is that the converse is not false, right? But it's not telling you anything about the actual
Okay.
problem. Right? So by doing this trick here, which is really what enables structural analysis, you're allowing for more variance than you originally had.
Mhm.
So if something is reachable here, it's not said it was reachable here.
Right, okay, it's not.
The converse holds, though. If it's reachable here, you will certainly see it here.
Right, okay, so it's this gives a necessary but not sufficient condition for reachability.
For reachability.
So you can detect failure to reach a marking, but not possibility.
I mean, also there's a problem about reachability. So the initial marking is part of the specification in reachability, right? Is the initial marking reachable from this, sorry, is the target marking reachable from this initial marking?
Yeah.
When you do structural analysis, you're sort of forgetting initial marking. You're
Yeah.
doing things for arbitrary initial marking.
Yeah.
So what you could say is, yes, there exists an initial marking such that the target is reachable, but then that's trivial because you just take the target to be the initial marking.
Yeah. Or but like reachability as defined by two different markings, is there a path from one to the other? Like that's the way you could phrase that problem. And you're saying it's not.
So that's the thing, right? Structural analysis tells you things about there exists a marking or for all marking.
Yeah.
It's sort of, it's a, I mean, it's the information you can derive by looking at the structure of the net without the tokens, right?
Yeah.
This is why it's called structural analysis, right? And it's there that you can effectively use linear algebra. The moment you start using initial markings, then you have to put an end here, K, what's the
Right.
K? And yeah, it makes just the problem, you're back with the initial issues of complexity and what's the K? Is it computable?
Yeah.
Is K an Ackermannian function of the number of places, that kind of stuff?
Okay, are there any further questions? If not, let's thank Adrian again.
Well, thank you for having me.